So the last section we're going to look at for this week, which will be split into two pieces, is 11.2. And this is on what we call finite and infinite series. So the main idea of a series is now you're not just looking at a sequence, but you're adding up every number in the sequence. So that can be a little bit more challenging. It depends what kind of series we're looking at. But today we're going to focus on a finite series. Next time will be infinite. And if you're wondering, well, wait, how could you add up infinitely many numbers? You can sometimes. It depends on the numbers. But it is possible to add up infinitely many things. Sometimes. All right, so in the last section, we used this kind of notation to denote a sequence. We used a lowercase letter, and then a subscript on that letter that indicated the position. So let's pretend like this was our formula for our sequence. A sub n equals 2n minus 1 squared. Let's write out some of the terms in that sequence. I'll just do the first 6. Those numbers I just wrote, they just represent position. So if we plug in 1, and you know what we'll do? Let's just simplify what's inside the parentheses. Let's leave the exponent of 2. We won't do the exponent out. So if you plug in 1 for n, what do you get inside parentheses? 1. So we get 1 squared. Right? What if you plug 2 in the parentheses? So we get 3 squared. And if you plug in 3? 5 squared. Yeah, so what the pattern ends up being is odd numbers squared. It's easy to see if you don't square it. If you do these out, and like if I gave you this list of numbers, 1, 9, 25, 49, I mean, most of you could probably still figure out that that's odd numbers squared, because you'd see that these are all numbers you can take square roots of. But it might take you a second to figure out that it's just odd numbers squared. That's why I left it like that. So questions on those terms? Okay. So now, what we're going to look at is adding some of these terms up. Capital S with a subscript n. That stands for the sum of the first n terms in the sequence right there. So for example, S sub 1, well, that means to add up the first 1 terms in the sequence. Well, that's just the first term. S sub 2 would mean to take the first 2 terms in the sequence and add them up. What would S sub 3?
You add 1 squared, 3 squared, and 5 squared.
1 squared plus 3 squared plus 5 squared. Yep. And then S sub n would be like 1 squared plus 3 squared plus 5 squared plus 7 squared, all the way up to whatever the last one is. So now let's do some of these out. Let's say I'm going to add one more to it. So let's write out S sub 1, S sub 2, S sub 3, and S sub 4. So what I'm doing now is I'm going to make a new sequence right here. But each position in the sequence is going to represent a sum of numbers. This is going to represent the sum of the first number, the sum of the first 2, the first 3, and then the first 4. So what do we get if we add up the first number in that sequence? You just get 1. Okay. What if you add up the first 2 numbers in that sequence? You get 10. And if you add up the first 3 numbers? 35. And let's do one more. If you add up the first 4 numbers in that sequence. So we got 35 plus 49. 84. Okay, so what this is called a sequence of partial sums. And the goal now is to try to predict a pattern in these numbers, 1, 10, 35, 84. Because if I can figure out a pattern here, then I could tell you, say, what S sub 70 would be if I added up the first 70 terms in that sequence. But the trick is going to be, can I figure out a pattern with 1, 10, 35, 84? That can be hard to do. But is there any question on how I got 1, 10, 35, 84? Okay. So each one of these numbers, S sub 1, S sub 2, S sub 3, S sub 4, each one of them represents what we call a finite sum. It's finite because I only added up a certain amount of things to get that. That's not infinitely many things. It's only 3 things. That's only 4 things. That's only 2 things. So each one of them is called a finite series, since there are only a fixed number of things you've added up to get that number. And the next part, actually, we already did. If you take all these S sub n's and you start writing them with commas between them, like S sub 1, S sub 2, S sub 3, S sub 4, what you're creating now is a sequence where each number in the sequence is a sum. And that's called a sequence of partial sums. So nothing here is infinite. It's just a finite amount of things you're adding together. Okay, so I'll write it one more time in general, how you get S1, S2, S3, and so on. S1 is just the first term in your sequence, the original sequence of numbers. S2 is the sum of the first 2 terms in your original sequence they gave you. S3 is the sum of the first 3 terms. S4 is the sum of the first 4. Okay. All the way to S sub n. And this is the first partial sum, second partial sum, third partial sum, nth partial sum. The nth partial sum would mean to add up every term in your original sequence, starting at the first term and ending at the nth term, whatever the nth term is. Any questions on that? So finding a pattern in that sequence, like the numbers we just had, I forgot what they were, like 110, 35, 84, something like that. That could be a tough pattern to figure out. Okay, there are certain kinds of well-known patterns we're going to work with that are easy to figure out, but not every pattern is really easy to figure out.
Is there always a pattern between them?
If your original sequence was generated from some formula, then yes, there should be some type of pattern you can get in this list of numbers somehow. If you just pick random numbers, then no, probably not. But if those are generated from a formula originally, we should be able to get it. And we could type that in. I think I showed you that website yesterday, maybe. Did I bring it up?
The music one?
Yeah.
Yeah.
So if you go on to OEIS, the Online Encyclopedia of Sequences, if you type those 4 numbers in, you'll actually probably get more than one answer. If you type 5 or 6 numbers in, you'll probably get a formula that would predict those numbers. Maybe it's something we would understand, maybe it's something that's really complicated and we don't quite get it.
I don't know what the formula is, but I know what the pattern is. It's from S0, it increases by 1 squared, then by 3 squared, then by 5 squared, then by 7 squared, so it's like the same pattern.
Yep, because that's coming from the original sequence of numbers that generated it.
Are you telling us to go to online encyclopedia of series or whatever for our homework? As a helping hand website?
I'm not sure it'll really help you for the kind of problems I'm going to give you.
Oh.
Because you won't be able to use it on the test anyway.
Dang.
So, okay, we did that. All right, let's look at this. So we got to start looking at a different kind of notation to write things down. Because if I want to write down, pretend I want to write down adding up 1,000 numbers. Well, I would rather not have to write the number plus another number, 1,000 times. There has to be some kind of notation that I could use to add up or to at least represent what I'm thinking. And the notation we're going to use is called sigma notation. Now, let's say I wanted to represent adding up every number from 1 to 1,000. And I don't want to write 1 plus 2 plus 3 all the way to plus 1,000. What I could do is this. I'll explain what this is. I said 1 to 1,000. Something like that. All right. What this represents is usually you have 3 parts to something in sigma notation. You have a starting point, stopping point, and then a formula that you want to use that's going to generate values you're going to add up. Okay, so let's look at it again. So let's say we had a sequence, and these were the terms in it. A1, A2, A3, all the way up to AN. And I don't have a specific formula for the sequence. I'm just there would be a formula there. This is basically telling you the first number that you're going to plug into this formula on the right-hand side. This is telling you the last number you're going to plug into the formula. So in my example, if I write it like this one, you can use different letters. I'll use K. So K equals 1 to 1,000. And the formula we would use, let me just make sure I use the same letter that I'm going to be using later on. Okay, I'm going to use K on N. I'll just use K. A sub K equals K. So what that means is you start by plugging 1 into this formula. There's not much to do in that formula. You basically plug the number in and you're done. And you write it down. Then you add 1 to the starting value, and that's how you get the next value. So the next value you plug in is 2. Plug it in for K, and write down the result when you plug it into that formula. Plus, and now you do 3. Plus, and then when you get up to 1,000, and you plug that in for K, that's where you stop. Now, sometimes this formula is more complicated. Sometimes it's like, K squared plus 3. So it's not just as simple as just plugging in the number and then writing the number down. You might have to plug in a 1, square it, and then add 3. Plug in a 2, square it, and then add 3. Okay. So, depends on the formula. So this, if you want to pronounce what it says, is you start by pronouncing the sigma, which is the sum, from the starting point to the stopping point. So from K equals 1 to N, and then you say of, and you write the formula that you want to use to generate the numbers you're going to add up. This is called the index. Okay, the letter that you use right here. That's called the index. The index doesn't have to be a K. It could be different letters, but K is used quite a bit. And the index has to be a number. It has to be set equal to a number. generally you start at 1. But you don't have to. You can start at 0. That comes up sometimes. Or you could start at 2. You might think, well, wait, I thought you said sequences didn't have a 0th term. Well, this doesn't represent necessarily a term. It's a number you're plugging in to get a term. Okay? So whatever value this starts at, like let's say it started at 10. Well, the first term in this formula now is going to be generated by plugging 10 into that, whatever that is. The second term would be when you plug in 11. The next one would be when you plug in 12, and then 13, and then 14, and then 15. So this one just starts at the number 10. Yeah.
So negative numbers also.
Yeah, you could start with a negative index, definitely. It doesn't mean that you're starting with the negative third term. It means negative 3 is the number that generates the first term. Negative 2 generates the next term. Negative 1, 0, and so on. But 1 and 0 are probably the most common numbers that you start with. Right, let's actually write this one out.
Sorry, can you scroll back?
So this particular sigma is representing a fifth partial sum, meaning you're adding 5 things together. You're going to start with your index at 1. You're going to stop at 5. And you're going to plug in every number, 1, 2, 3, 4, 5, into that formula. And write down all the results you get and add them together. Okay, so let's start with 1. If you plug in 1 for k, what do you get in that formula? 5. Plus, what's the next number we plug in?
7.
The next number would
2.
2, and you get 7. The next number you plug in, 3, and you get 9. Plug in 4, you get 11. And now we've reached the stopping point. You do plug that one in now. So when you plug in 5, you get 13. So this means that. And I'm going to write this down in a second. But on the left, it's called sigma notation. On the right, that's called expanded notation. So sigma notation doesn't give you a quick way of actually doing anything. It gives you a quick way of writing down what you're thinking of doing. Like if I wanted to add up every number in this formula from 1 to 5,000, well, I could express that idea very quickly. Doesn't mean I can do it very quickly, but I can express what I'm thinking quickly and very compactly. And there actually is a way to do it very quickly, but we'll get there. Okay, any questions on that? This is what I just told you. So when you write something with a sigma, that's sigma notation. When you write something actually doing it out, that's called expanded notation. Now, you'll probably also notice that as I write my sigmas, unless I take a lot of time to write them nice and neat, that's how it should look. Mine eventually start looking like this when I write them fast. That's my sigma. Now for today, this value right here at the top is always going to be some type of number, or it could be a letter that represents an unknown number. But it will be essentially a stopping point. If we put something like this on top, that's what we're going to look at next time. This represents no stopping point. You continue to add up numbers forever. And that gets into an infinite series. Okay. Any question on the difference between sigma notation and expanded notation? So let's write how we would expand this one out. When you don't know where to stop, you do stop somewhere. You stop at n. But we don't know what number n is. Just write out the first three. Then we can do like a dot, dot, dot. And then we'll do the last one. Okay. So what's the first number we plug in for k?
1.
1. And what do you get when you plug in 1?
25.
So 2 times 1 is 2 plus 3. You could leave it as 5 squared. Or you could do 25. Either way. I'm just going to leave it as something squared. Okay. What's the next number we plug in?
2, and then you get 7 squared.
To get 7 squared. A lot of times I leave it squared if I want to try to look for a pattern that's easier to see without doing the square out. Okay. What's the next one going to be?
3.
3.
9 squared.
And we get 9 squared. Okay, we've done enough to establish kind of what's going on here. Now we're going to do plus dot, dot, dot means there could be a bunch more. And what's going to be the last value that we plug in? N. And what do you get when you plug in n?
2n plus 3 squared.
So that's how you would expand that out. This is not infinite. This is finite. It stops right here. What number is n? I don't know. But it does stop somewhere. Any questions on how we expanded that out? Okay. All right, let's look at some different properties and like things we can do with summations. This property is kind of like distributive property. If you have two sequences that you want to add together, okay, you can do it two different ways. And I'll show you with some numbers. You could add the sequences together term by term, the first one to the first one, second to second, third to third. The sequences have to be the same length generally to make that work. And then you can add up all the numbers that you get after doing that. Or another way you can do it is if you want to add two sequences together, you can take all the sequences in the first one, add those first, take all the numbers in the second sequence, add those second, and then take those two numbers and add them together. And you'll get the same result. Let's make up a sequence and just try it. Short, simple sequence. Let's say A sub k is the sequence 1, 3, 5. And B sub k is just the sequence 2, 4, 6. Let's do it this way first. So that says to add the sequence together term by term. A sub k plus B sub k. Okay. What would the first term be in the sequence A sub k plus B sub k? 3. And then the next one? 7. And 11. Okay, so now we've got this. Now this says add up all the numbers you just wrote down. Okay. So what's 3 plus 7 plus 11? 21. Okay, so you get 21 doing it the way on the left. Okay, now the way on the right says forget about sequence B for a minute. Just add up all the numbers in sequence A. So let's just do this. If we add up all the numbers in sequence A, what do you get?
9.
So that's 9. And then if we add up all the numbers in sequence B, 2, 4, 6, we get 12. So we have a 9 plus a 12. What's 9 plus 12? 1. So it basically just gives you two different ways to add sequences together. It's kind of like distributive property. Well, if it works for addition, it also works for subtraction. It's the same. You really could just take rule 1 and you could just put like a plus or minus if you didn't want to write the same thing twice. Rule 2 is with a minus. I'm not going to go through that. Any questions on rule 2? Okay. Well, rule 3 is a little bit different. Rule 3 has to do with multiplying something by a constant.
Right. Sorry. Take a step back for a second. Where did we get the 9 and 12 that we added together for the final step of the last problem?
That was when you add up all the numbers in sequence A, 1 plus 3 plus 5,
Okay.
and then 2 plus 4 plus 6 is how you get 12. Okay, so what if we want to multiply by something and add? Well, you can do it 2 ways. This is almost like a scale factor. If you wanted to take a sequence and say, add up everything doubled, you can do it 2 different ways. First, you could double each number in the sequence and then add them all up. Or you could add up each number in the sequence the way it is and double it after. But you're going to get the same thing both ways. Let's do it this way. Let's pretend C was 2. What would, if this is A sub k, what would 2 A sub k be? 2, 6, 10. And now the sigma symbol means to add up everything that resulted from that formula. So what's 2 plus 6 plus 10? 18. Now, let's do it the way on the right. Let's add up all the numbers in the sequence first, and then double it after. So what do you get if you add 1, 3, 5? 9. And now double it after you do the sum. Still get 18. So anytime we can take something that's inside the formula for a sigma and pull it in front of the sigma, that makes the sigma simple. And that's really the goal. We would rather not have complicated things in the sigma. We'd rather have simple things, okay? Like a single sequence instead of 2 sequences, or a single sequence instead of a sequence that's been multiplied. Okay, we want to try to get the sigma as simple as possible. So any question on those 3 rules? Okay, so we can use those rules to basically take 2 separate sigmas and combine them into 1. In order to do that, you have to start at the same index in each sigma, and you have to stop at the same spot. If you had something like this, you can do it, but you have to do what's called reindexing. You have to fix it so k is 1. I'm not going to talk about a reindex for this problem. I might with something simpler, but not with this one. All right. So when you combine these together into a single sigma, what you have right there is basically like this. I'm trying to change it back to that. So I'm going to combine the 2 sequences together. And how am I going to do that? I'm just going to combine like terms. Whatever the start and stop was before, keep the start and the stop the same. Okay, so it's going to be starting at what number?
1.
Stopping at
And
n. And now just combine like terms with that and that. So let's start with our squared term. What are we going to get for that?
6k squared.
So 6k squared. Yep.
Minus 2k.
Minus 2k.
Plus 3.
Minus 4 plus 7 plus 3. There you go. So that's how you can combine 2 sigmas into 1, which that's also a better thing to do because it's easier to deal with 1 than 2.
Okay, so we literally just added 2 combined.
Yep. Any question on that? Okay, so again, the sigma notation is great, but it doesn't really give you a fast way of doing anything. It just gives you a fast way of writing down what you're thinking. But if I wanted to add up every number, that's what this represents, every integer from 1 to 10, I would still have to do that up. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Now, if you think about it, you might be able to be a little bit clever with adding up 1 to 10. Not that adding up 1 to 10 would take that long, but let's pretend that you were adding up, well, let's just do 1 to 10. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Does anybody see a kind of a clever way that you could add up the numbers from 1 to 10 without actually adding them up? Kind of looking for maybe a pattern that you could repeat over and over. Well, it's going to be adding them up, but it's not going to be adding them up in the order 1 plus 2 plus 3 plus 4. We're going to add them up in a different order that's going to give us something repeated that happens, yeah?
1 and 9, 2 and 8.
1 and...
9. Oh, 1 and 10.
I would add 1 and 10. And what does that give you?
11.
11.
And then 2 and 9 is 11.
2 and 9 is 11.
And it repeats 5 times.
Yeah. 3 and 8 is 11. So if you look at how many pairs of things you're adding up, that's 55. Because you added up 5 pairs of things that add up to 11. So now you could apply that idea if you had like 1 plus 2 plus 3. And then this would be like 100, 99, 98. 1 plus 100 is how much? 101. And then 2 and 99? 101. So it's just a matter of figuring out how many pairs of 101s you would have, depending on whatever your start and stop is. And that's kind of a clever way to figure it out.
Would you just define how many pairs you have? Would you just divide what your stop number is by 2? Because you're going in pairs.
Well, you divide how many terms you have by 2. Because you might start at 8 and stop at 200. So then it wouldn't be 100 pairs in that case. And then if you had an odd one left over, well, you just have to deal with adding that one in by hand at the end. And again, these are like clever little tricks. It still doesn't answer the question kind of in general. How are we going to do that? Because that trick doesn't work all the time. Pairing them up at the ends and working your way to the middle. So we're going to look at some formulas that do work. And we're going to look at one specifically for probably 3 types of formulas. This will be one of them. Squaring it will be the highest we look at. And then we're going to look at one that's even a little simpler than this one. Excuse me. Thank you. Right, let's look at this. What I want to do is see if we can figure out a pattern for adding up the sum of the first n integers. That means like 1 plus 2 plus 3 plus 4, as high as you want to go. I'll do it out up to 6. Maybe I'll do 7. All right. If that's my sequence of numbers, what do you get if you add up the first 1 terms in that pattern? 1. Okay. What if you add up the first 2? 3. And if you add up the first 3? 6. You're basically just adding that number to that to get that. So the next number? 6 plus 4 gives me 10. 10 plus 5? 15 plus 6? And 21 plus 7? 28. So now the goal is to figure out a pattern in the numbers 1, 3, 6, 10, 15, 21, 28.
So how do we get those numbers?
Just adding up the first n numbers in that expression. Now, well, we've learned about 2 kinds of patterns. We learned about arithmetic and geometric. Let's see if it's either one of those. Do you add the same thing each time to get from one to the next? No. Do you multiply by the same thing each time to get from one to the next? No. So it's not an arithmetic, it's not a geometric pattern. The way we can figure out what it is we're going to do something by hand, and then we're going to use the calculator to help us. Let's write down 1, 3, 6, 10, 15, 21. That's enough. I want you to find what's called differences. What's 3 minus 1? 2. And 6 minus 3? 3. 10 minus 6 is 4. That's 5. 6. Okay, now I want to do it one more time. Let's find the differences again. This time you're going to get a row of all what?
Ones.
All ones. When you reach a row that's all constants, which sometimes you never do. If you tried this with the Fibonacci sequence, you'd never reach a row of all constants. You'd keep getting the Fibonacci sequence every time.
That's kind of crazy.
It wouldn't work. But if you can make this difference tree, this tells you that, and you get a row of constants at some point, this tells you that the formula to represent all these numbers is a polynomial. Specifically because you had to do it 1, 2 times, it tells you it's a polynomial with an exponent of 2. So that means the formula to predict these numbers is a quadratic. So we know that. Okay, it is a quadratic. To figure out the quadratic, well, there's different ways to do it, but we're going to use the calculator. And we're going to plug in these data points. This is the only formula that I'm going to figure out by hand. Well, I'm not even doing it really by hand, but I'm kind of using a calculator to help. The other formulas, I'm just going to give you what they are. So we're going to type in all these numbers. 1, 2, 3, 4, 5, 6. And the other part of the coordinate, 1, 3, 6. That's probably enough, but we'll just type them all in. Okay, now we're going to tell the calculator to look for a pattern in these numbers. And we know what kind of pattern we're looking for. What kind of pattern did I say that those numbers are going to be?
Quadratic.
I said it was going to be a quadratic. So I'm going to tell the calculator to try to look for a quadratic pattern in those sets of numbers. And so let's have it look for a pattern and see what it tells me. Okay. It gives me this. It says the formula is 1/2 x squared plus 1/2 x. Well, we can do a little better. We can simplify that. What can you factor out of that?
1/2.
You could factor out a 1/2. And multiplying by 1/2 is the same as dividing by what? 2. Let's try it. Now, I know normally we use the letter n. I just used x because that's what the calculator used, but we're going to write it with an n when we do it. Let's see if we can predict the third number. We should get a 6. What's 3 squared? 9 plus 3
12.
divided by 2. 6. Let's try to predict the fifth one. We should get 15. What's 5 squared?
25.
Plus 5
30.
and 30 divided by 2? 15. So we just figured out a formula that predicts the sum of the first n integers. So now, if you wanted to add up, say, the first 10 integers, when we did this, let's go back. What did we say this added up to?
55.
This adds up to 55 using that clever trick. Let's try plugging 10 into the formula. What is 10 squared
100.
plus 10? And what's 110 divided by 2? 55. There's your 55. So this is the formula that predicts adding up integers. Okay, we're going to look at integers, we just did. We're going to look at constants, which is a little easier. And then we're going to look at adding up things that are squared, like 1 squared plus 2 squared plus 3 squared plus 4 squared. As high as you want to go. so how would it work if it was a constant? Let's say you wanted to add up from k equals 1 to 8 of the number 3. So this is your formula on the right-hand side. When you take 1 and plug that into this formula for the k, what do you get? 3. There is no k. This is just a constant. What about if you plug 2 into that formula for k? You get 3 again.
There's no, it's just 3.
And how many times are we going to get 3? How many?
8. Oh, yeah. I mean, it's just turns out.
So instead of writing it like that, does anybody see what you can do here?
3 to the
Multiply 3.
Yeah.
times 8.
All you have to do is multiply 8 times 3. So that's the pattern if you want to add up a constant that many times. Adding the same thing up over and over is called multiplication. So you just have to multiply those two together. And that is the first formula I'm going to show you. If you want to add up a constant that many times, all you have to do is multiply the constant times the number at the top, and that's the answer. So what we're doing now is we are coming up with formulas that get rid of the sigma. We don't really like sigma. Right? Say it's okay, I mean, if you want to write down an idea, but it's not helpful for calculating anything. It doesn't speed anything up. So if we can use a formula to replace a sigma, that's how we want to do it. Okay, the next formula, this is the same one we had written down before. I used x squared plus x over 2. This is n times n plus 1 over 2. That's generally how you write the formula for adding up the first n integers. You can FOIL this out if you want to. That's just how it is in the book. So this formula gets rid of sigma if the formula involves adding up an integer. Now, you can also apply it to something like that. You might say, well, how would you do it if there's a 3 there? Well,
Multiply everything by 3, right? No.
think back to this rule right here. If there's a 3 here, where can you put it?
In front of
You can put it in front, and then it's really the same problem. You do exactly what you would do, but once you get your answer, you just times it by 3 at the end. Right? So these formulas work even if this is a little bit more complicated. To use this one, though, it has to be something with k to the first power. If you had something with k to a second power, it's a different formula. What was the highest exponent in that one? It was a 2, so it was a quadratic. The next one, the highest exponent is a 3. And in order to figure this out, this would be a tough one to figure out. You would have to make that difference true. You would see if you did it 3 times, you would end up with a constant, which would mean that your formula is a cubic. Then you could type all the points in on the calculator, and it would give you something like this, but in a foiled out version. It wouldn't be factored. How would you get that by hand? I'm not 100% sure. I haven't done that in a while.
Twice is 6.
It's just the way it works out. I don't remember how to prove this by hand. But that's as high as we're going to go. I wrote one down for cubed. And could you at least guess what the highest exponent would be in it?
4.
Yeah, it is to the 4th power. Because if you FOIL this out, you get an n squared times an n squared. But we're not going to do the cubed one. Squared is as high as we're going to go.
How do you take those numbers into the calculator to get the formulas stuff?
to type. Well, you're not going to have to type in anything like this on the calculator. That won't be part of what you have to do.
Is there a sigma button on the keyboard?
Yeah. Your job, though, is going to be to change this into that. Which that's why the calculator doesn't really help you do that. Okay, but these are pretty much the three things you got to look for. Either adding up a constant, adding up something that just has a first power, or something with a second power. Let's try, I have that one, and yeah. Let's try this one. We've got to make this look more like these. So the first thing we want to do is try to simplify this. And the way we're going to simplify it is we're going to split this up into two different sigmas. Let's start with this one and this one. They're both k equals 1 to n. What do you think is going to be my formula for my first sigma?
-2.
What is it?
-2.
Yep, it's going to be a minus 2k. And the formula for my second sigma? 3. So what we just did right there is this one. We took two things that were added together and we split them apart into two different sigmas. Now I'd like to do something else at the same time. This second one is fine. This is one of our formulas. You're adding up the number 3 this many times. We can work with that. But this one has a k, but we don't have a formula that has a -2 with a k.
Would we pull the -2 outside the
Yeah.
sigma?
So what we really want to do is put that -2 in front. And now we have something we can look for on our formula sheet. And we have something else we can look for. We're going to substitute for those two red boxes. What can I substitute for that first red box? Yep, we can substitute n squared plus n over 2, because that's what it would simplify to. We kind of proved that with the calculator. And what can I substitute for that last box?
3n.
Say it again.
Just 3n.
Just 3n. Whatever your constant is, times how many times you're adding it up. Now, just combine like terms and that's your answer. Well, this actually is kind of nice. These 2's are going to cancel. And we have a negative we need to distribute. What do you get when you distribute that negative?
This is -n squared minus
Negative n squared minus what?
4n. You combine it then, oh no, you do it first.
Well, do that, so minus n.
Yeah. Okay.
So plus 2n.
Yeah, I did that.
And what you just found is a formula for adding up terms, okay? If you wanted to do this, let's say I wanted you to add up everything from 1 to 500. You would have to take the number 1, plug it in for k, and write down what you get. Plus, take the number 2, plug it in for k, write down what you get. All the way up to plugging in the number 500 for k, write down what you get, and now add up all 500 of those calculations you just did. Now, in order to do that, all you have to do is plug the number 500 in right there, and you're done. 500 squared, make it negative, and then add 1,000. And that would represent adding up all 500 numbers in that segment. Just by using a formula you can plug into it. So doing it this way, it's kind of like recursive. you have to know every single term you want to add up all the way to the last one. Doing it this way, you can just jump to whatever term you want to add up. You want to add up 500? Plug in 500. That's the difference. So, any question what we did there? Okay, I'm not going to worry too much about the squared ones. The math just starts to get a little messy because you have to FOIL this all out. If I had to do squared ones a lot, I would probably write a FOILed version of this on like a piece of paper that I could use. But I would say these are probably the most important to focus on, to be able to do what we just did. Okay, so let's look at the last thing. Yeah, that's the same as the last one, but I said we're going to skip squared. Let's look at this one. So this is a formula for adding up terms in a kind of sequence we talked about yesterday. A geometric sequence. Let's say you had the numbers, I don't know, let's not make it that big. 2. And then let's take half each time. So I get 1, 1/2, 1/4. Let's just start there. Does everyone agree that's a geometric sequence? Okay, let's add it up. We can do that by hand. What's 2 plus 1 plus 1/2 plus 1/4?
3
3
3/4.
3 3/4. Now, let's see if this formula gives us the same result. This is a formula for adding up the sum of the first n terms in a geometric sequence. You have to know 3 things. What's the first term? What's the common ratio? How many terms do you want to add up? Right? Well, how many terms did we add up in that sequence? Okay, so we added up 4 terms. What was the first one? 2. And what's the common ratio? We're multiplying by 1/2 each time. And then that's all over 1 minus 1/2. Let's do that out and see if we get 3.75. We can simplify it a little bit. What's 1 minus 1/2? 1/2. Okay, let's see if we can type that in. All right, so you're going to need some parentheses. Let's start with double parenthesis. Let's do 1 minus, instead of 1/2, I'm just going to do 0.5 raised to the 4th. Okay, there's my numerator divided by, what's my denominator? 1/2, or just 0.5. And I'm going to put the 2 at the other side just because it's easier. I can put the 2 in front, but I need to do times 2. And if this formula works, what should I get?
3.75.
3.75. Wow. I do. So adding up 4, that's not that hard. But let's say I wanted you to add up every number in this sequence for the first 50. I want to know what the first 50 add up to. Well, if you want to do the first 50, it's not really any harder than doing the first 4. Just change that to a 50. That's all you have to do. Now you can add up the first 50 terms. But what do you notice about what's happening to each term?
It's getting smaller.
They're getting smaller and smaller. So next you're going to add an 8th, then a 16th, then a 32nd, then a 64th, then 1/128th. So eventually what you're adding is going to be so small that it doesn't really make a difference anymore. And the sequence starts to, that's not completely accurate, but it starts to approach 4. It's really 3.9 repeating. But it ran out of decimals. Okay. If I didn't use 50 and I used something like 10, you could probably see better that it's approaching 4. 3.996. But that kind of gives you a hint is if you add up 5,000 terms, it's still going to add up to 4 because the terms you're adding each time are so small they don't make a difference anymore. That's how you can add up infinitely many things. And you get an actual number as an answer. Only if the things you're adding get smaller each time. If you had something like this, then no. Because what you're adding each time is growing, it's doubling. If you add up infinitely many, you're just going to approach infinity in that one. Right, so that's the formula for adding up a finite amount of terms in a geometric series. That's all that this works for. Just a geometric series. Any questions on that? Okay. So, yeah, I'll leave one like that for you. But the thing you got to figure out here is what you multiply by each time. What's your first term? And how many do you want to add up? And you can figure that out. So 12th partial sum means to add up the first 12. And what are you multiplying by each time?
1/3.
Yep. So r is a third. First term is 2. N is 12. Fill them all into that formula, and you'll get your answer. Okay. Let's see. So, I'm going to do 7, 8, and skip. I can rewrite it in a second, but we're going to skip 9, 10, 11, and 12. And then the rest is fine. So that's going to end up being 1 through 8, 13. There you go.